Good evening. We're the CSUN Aero team. We're excited to present to you our design for the advanced class competition. We'll start with project planning. We approached our project by simulating a fully functional aerospace engineering firm, where we implemented a hierarchical leadership structure, starting off with our faculty advisor, who simulated the role as CEO of the company, our team captain, who simulated the role of chief executive engineer. He communicated with group leads, and group leads communicated with their individual engineers and their teams. Because we understood the importance of the competition rules, we also incorporated a compliance officer. He was he was in charge of safety inspections and quality assurance. And following our approach, we also created a timeline with our milestones in order to get to our competition. So during the design, we needed to implement the constraints. Without the constraints, we have a free space for design, but as we know, engineering projects do not consist of that. So our first constraint was performance, and performance, this was implemented by the competition. Our weight, we used the competition scoring to decide on our weights, and we also divided the weight within the teams. Each team had a different weight, and we also incorporated a 7% error margin for any changes that had to be made. As previously stated, one of our constraints was our timeline. Cost was also a constraint. We started with a budget of $11,000, but we also got some support from the private sector. And last, manufacturability. If a design could not be manufactured, then it was not considered into our design. All of these constraints left us with our team's design envelope. Our design fell within this envelope. We created a system level diagram. This was a dynamic engineering tool, and we used it to help us understand our project better along the way. On the right, we have a legend with all the connection components. And our diagram is centered around the fuselage, branching out to the wing system, the tail system, the propulsion system, following by the landing gear, the cargo, and our servo system, our control systems. Our system level diagram was iterated and updated upon changes. So during our analysis and synthesis part, a lot of trade studies were done, and a lot of configurations were selected. So our evaluation criteria was based on the constraints from our engineering envelope design. We started off with the wing, and we decided that rectangular wing would be better for our design. With the tail, we also had 3 options, and it was decided that the standard tail would be better for this design competition. Following with the landing gear, where we chose a tricycle landing gear. And last, our fuselage, where we chose a rectangular shape, keeping in mind the weight, the packaging, as well as the structural integrity. So now it was time for vehicle sizing. We started with our requirements of a lift, cargo, and avionic requirements, followed by our airfoil selection, and our selection of general aviation single prop. The airfoil selection and the lift requirements gave us our wing dimensions, and our cargo requirements and avionic requirements gave us our fuselage dimension. With this, we were able to get the dimensions of our vertical and horizontal stabilizer. Aerodynamic and stress analysis were coupled and were frequently iterated.
The wing was sized based off of the lift requirement from the rules and our weight determination, as well as the aerodynamic choices we made, for instance, the assumed speed of 30 miles an hour and the choice of the Sealy 1223 airfoil based on one of the trade studies we performed. We rewrote the coefficient of lift equation to be a function of aspect ratio and chord length, and combining these two, we informally optimized the aspect ratio by populating sets of tables in order to narrow it down to 12. We then formally optimized the angle of attack by writing a code in VBA to determine an alpha equals 9. And then we solved analytically for the span and chord length to get the final size of the wing. The horizontal stabilizer, meant to react the pitch and lift from the wing, was offset by the wing downwash and also other wing dimensions, and was based off of the horizontal stabilizer volume coefficient and controls the pitch stability. The vertical stabilizer had a similar procedure, and you can see in the free body diagram that was designed to react against the propeller torque for roll stability. To summarize the takeoff performance, the takeoff time is about 9 seconds in about 230 feet, and we did this using a spreadsheet calculation that incorporated all four major force inputs on the aircraft. The stability and control of the aircraft is governed by the roll, pitch, and yaw. And to control the roll, we sized the ailerons initially based off of industry recommendations, and then we drew the rolling free body diagram for the aircraft, and we determined the dimensions and the roll rate based on the dynamics of the free body diagram. Once the roll rate was determined, if it was acceptable to a pilot and was manufacturable based on its size, it was incorporated into the design. If not, it would be iterated. The elevator to control pitch was designed for level ascent during takeoff. And the rudder, because we did not have the facilities to perform the required empirical testing, we went with the industry recommended values initially, but found later that a crosswind analysis showed we could withstand a crosswind of up to 46 miles per hour with those given values. The servo requirements in packaging, the servos exceeded the maximum torque requirement on the aircraft, and also are packaged along with the subsystem that they belong to for modular detachment and all our fasteners and bolts. Now that we have our aerodynamic loads, we can move on to the stress analysis. So we used composite laminates for major structural components for their desirable strength and stiffness, and we used polymers and simple woods for low load or non-critical members. We used the Tsai-Hill failure criteria for composites and the distortion energy theory for ductile metals. We used 3D solid models and accurate weight assignments to control and predict and account for the center of gravity in our aerodynamic design and our structural analyses, which were coupled. In the figure below, to determine the failure modes for these analyses, we incorporated to determine the failure modes for these analyses, we first looked at the load path based on the geometry, and then applied the correct failure criteria for that material. And only once the design met the minimum factor of safety or exceeded it, did it continue with the design. So here's some examples of the stress analysis that we performed. Here are 5 of the locations, though there are many. For example, the wing, which is composed of an E-glass laminate, for the analysis to check for bending, met and exceeded its minimum factor of safety using the Tsai-Hill criteria. Some of the experiments we had to perform throughout the manufacturing and assembly and flight testing phase were to test the engine or the propulsion subsystem overall for maximum thrust and for fuel consumption. We tested the control system on a trainer platform as well as on the benchtop to test it on the ground and in the air. We checked the aircraft structure in multiple ways, but 2 of the main ways were with deflection tests using a simulated elliptical load using calibrated weights, and to check for the multiple glued joints by putting multiple peel and shear samples in a tensile testing machine. So we learned multiple non-technical and technical lessons along the way. To start, we definitely learned the value of efficient and effective time management, resource management, and overall project management, working with a team of people, and we'd also like to share some of the technical lessons we learned. First, that the system level diagram was an extremely effective and valuable tool that we developed early on in order to continually improve our understanding of our system. We realized partway through the project that we wanted redundant servos initially, but that measure, which initially was to mitigate risk, turned out to be counterproductive because of some technical issues that came up with servos. And while challenging, the implementation of composites definitely proved to be a very valuable choice and a very appropriate material selection for aerospace applications. And finally, nose gear steering was early on in the process traded out of our trade studies. However, we reincorporated it upon gaining more understanding of actual flight operations on the runway and requiring that extra controllability and stability during the flight testing phase. We'll take your questions.